Lecture of the final day. So the lecture is by Tarun, Maharaja Sayajirao University in Baroda. It's the same. Okay, the title is Human Generically Continuous Expansive Homoclinic Process are Ergodic. Thank you.
We already have witnessed quite a long and tight schedule, and I don't think I'll contribute to that. I just thought that there were quite a few lectures on Ergodic theory and related areas. But I think primarily it was Professor Sakai who gave a talk yesterday on smooth dynamics. There was a couple of short presentations yesterday. So I thought I will just give an outlay of what kind of things have been done and what is that we are interested in, rather than giving a straight proof of some of the results. The study of dynamical systems, as we've already witnessed, is either a continuous flow or a discrete case, and both have the transition. One can actually move from one place to another place, but I'll stick to discrete time evolutions. In smooth dynamics, we study the differentiable flows or maps, and in these situations, one tries to develop local information from the infinitesimal information provided by the differential. Among a smooth dynamical system, hyperbolic dynamics is characterized by the presence of expanding and contracting directions for the directive. These stretching and folding gives rise to complicated long-term behavior in these systems. The dynamics appears in many ways effectively random, even though these systems are completely deterministic in quite a few situations we've already witnessed. The various aspects of the complexity present in these systems makes it natural to study their topological structure, as well as the statistical or probabilistic aspect of the evolution, which the later part we've already witnessed quite a lot, as I said. The simple situation illustrating this crucial aspect, I'll take a couple of very simple examples. Let's look at this linear map. I think we have already come across, we might discuss this example. So here one can see the behavior on the horizontal axis and the vertical axis on the plane, which is acting. So I have eigenvalue less than 1, so avoiding circle, unit circle, 1 plus 1. So this is, so one can actually look at A inverse and look at its action there. So what one can see that this A inverse interchanges the role of expanding and contracting subspaces. The same analysis applies to any linear map without eigenvalues of the unit circle. Now, subspaces, but we can actually look into now the next stage is a sequence of linear maps, which is slightly more than what I have said, so one can go along this. This analysis of the linear situation can be transferred to study local behavior of nonlinear systems, where the stable and unstable subspaces are replaced by stable and unstable manifolds. The local stable manifold is characterized by the exponential contraction in forward time, and similarly one can do it for the unstable manifold. The strongest possible version of hyperbolicity is that the asymptotic contraction and expansion rates uniform. I think Mahesh was talking a while ago. The Smale school, he was referring to IMPA school, it's definitely the strong school in the smooth dynamical systems, and in 2010 satellite conference we had quite a few mathematicians of that place, including Dinalo and Bonatti and Antonio. I think this is, there's some, I'm sorry actually, some displacement. Because the last line is also not coming. So, sorry? This is a simple 2x2 case wherein you get the direction like this, and of course one has already talked about the rational and irrational rotations, and this situation naturally gets transformed. So these are all total automorphisms, and which has already been discussed, so I've skipped this. Okay, yeah, Smith's construction and variance law. Now, anosode diffeomorphisms are now known up to topological conjugacies. On the other hand, there are important examples of diffeomorphisms that are hyperbolic on a proper invariant subset. For example, Smith-Horsham. We discuss hyperbolicity of compact invariant sets. That is what is good. I'm aiming at that. A couple of historical results. Poincaré recurrence theorem, in this audience everybody must be knowing. So it talks about that area preserving diffeomorphism, and for a fixed point x outside the Lebesgue of set measure 0, orbit of x accumulates on x infinitely often. However, you don't get the global picture here. But on the other hand, if you look at this simple case, then also almost all are recurrent, but in this case we have a fairly complete picture of the total motion in this case. So what differentiates? The key point is that the hyperbolicity. So the notion, as we know, of hyperbolicity as of now is due to Anosov, and was subsequently realized by Smale in what he described as hyperbolic basic sets. I'll come to those basic sets. And the important and beautiful thing is that they are finitely many, and therefore there is a natural connection to subshifts of finite time, symbolic dynamics. So that we'll introduce this in the workshop. So yeah, the participants are aware of this. The terminologies are more or less same what Professor Sakai already described yesterday. So we talk of compact manifold, we talk of Ergodic point, which are hyperbolic, and yeah, these are the terminologies we will be using, and this hard point group transform, of course, is the standard one. And so this is a linear case, what we usually do. Then these are some simple examples. So this is how we define the stable and unstable sets. The stable set for f at point x, and unstable set. So this is how we define it. And I recall this stable manifold theorem for a point. The stable set is C1 injectively immersed copy of Rs, where S is the dimension of the space ESP, and this is the dimension of P there. And this is the definition you've already seen yesterday. Again, this is compact F invariant set. Lambda is called hyperbolic if the tangent bundle has a continuous DF invariant splitting, and if you can obtain the constant C, so that this happens, then this is the definition of hyperbolicity, and extension for this is the notion of dominated splitting. Right? A compact F invariant set lambda admits a dominated splitting if the tangent bundle has a continuous DF invariant splitting, and there is a constant C and a lambda, so that you can have this inequalities. Then this is dominated splitting. Then actually I also need. Actually, I'm trying to define homoclinic point and homoclinic classes, so I need these definitions. So, two submanifolds of a given finite dimensional smooth manifolds are said to intersect transferally. So, if at every point of intersection, they are separate tangent spaces at that point together generate the tangent space of the Indian manifold at that point. So, I have now illustrated, some of the simple situations. Manifolds, So, if the manifolds are of complementary dimension, the condition means that the tangent space of the Indian manifold is the direct sum of the two smaller tangent spaces. In the absence of transversality condition, the intersection may fail to be a submanifold, of course. Here are some examples I have listed. So, for example, curves transverse to surface intersects in a point, and surfaces transverse to each other intersects in curves. Curves that are tangent to a surface at a point do not intersect the surface transversely. We use this notion of transversal intersection to get to the definition of this. Now here is how to define the homoclinic point. A point x staying in this intersection, of course we exclude P, then it is a homoclinic point. and we say that they intersect transversally at x. Then if they intersect transversally at x, then we say that there is a transversal homoclinic point. And what Smale proved in 75 is that if f is a C1 diffeomorphism with hyperbolic periodic point P having a transverse homoclinic point x, then there is n greater than 0 such that Fn in a composition of f has a closed invariant set lambda containing x in P, so that the restriction is topologically equivalent to shift automorphism. This is what I was referring to a little while ago. So this is what he proved, and this lambda is hyperbolic for Fn. I wanted to define what is hyperbolic set. So this is how we get to it. An important consequence of the previous theorem is that the transverse homoclinic points of the diffeomorphism F are in the closure of the hyperbolic periodic points of F. This is very important. So therefore you get the invariancy there. I have this notation HF for an F denotes the set of hyperbolic periodic points for F. And then this is the OAP is the orbit that I am defining. I am extending the notions W sigma. Sigma stands for S or U, that is stable or unstable. So we're talking of stable and unstable points of sets for orbits actually. So these are termed as stable, unstable manifolds. Sometimes they are actually not, but there is a term like that. Now here is a relation on HF. We say two points are related if the sets we have defined are actually transversely intersecting, and this relation turns out to be equivalence relation. At the early stage, one has to do a little bit of work to show this. One has to use a lambda lemma to prove that this is an equivalence relation, and the equivalence class of P is actually the homoclinic class of P, and we denote this by a symbol. So yeah, as I said, this is closure. This is actually, this turns out to be the closure of the set of all points which are related. So it becomes invariant, and obviously it contains the orbit. Yeah, they are closed. They are topologically transitive, and this is also very important. Every transverse homoclinic point of a P is a limit of a sequence, so that each of them is homoclinically related to P. This is important. A long time goal in the theory of dynamical system is to describe the dynamics of big sets, a generic or residual. Mahesh was again referring to these sets in the space of all dynamical systems. Texito in 62, he proved that the set of all structurally stable C1 vector fields on a C infinity compact 2 manifold is open and dense, and in the totality of the C1 vector fields, it is open and it is dense. That was proved. And therefore there was anticipation that okay, such results may go ahead for higher dimension and so on and so forth, but it was soon shown to be not true. In 66, Smale showed that if dimension of M is greater than 2, then in general dynamical systems may not enjoy such nice local dynamical representations. In fact, Abraham and Smale in 70 showed that even omega stable systems are not dense. Omega stable, so one talks of a non-wandering set, therefore non-wandering set omega you take, and then one actually restricts to the functions. So omega, the non-wandering set is an invariant set. It is closed, it is non-empty, it is compact, so it becomes a natural invariant set. It contains, so interesting cases when it contains all periodic points which are dense there. So that is the most interesting case, and therefore one talks of omega stability and no axiom, no cycle condition, that is axiom A, one talks about that. So therefore this was very important observation that even omega stable systems are not dense. Of course, they did include the surface diffeomorphisms. By the end of 60s, even omega stable diffeomorphism on surfaces were shown not to be dense in CR topology, R greater than or equal to 2. And the R is equal to 1 case, I don't know. So Sakai may actually tell better, but I think it is still an open problem. This has been done through very original examples. The earlier case which I am referring to by Newhouse, he published a series of papers almost 8 to 9 years. He showed that there are residual subsets of open sets of diffeomorphisms whose elements display infinitely many saints, more technically, homoclinic tendencies lead to rich dynamics. That's what. Therefore, the natural aim is to have nice global presentation like the Institute did in 62. But so what? How far and how best one can go ahead? How large one can go ahead? To understand this global description of a dynamics, one has to go for some kind of indecomposability. So natural thing is, of course, in some sense you obtain indecomposable sets which are actually invariant with respect to the given type of dynamics. So the most natural definition what one gets is that of the transitive sets. So if a system is non-chaotic, I have not defined what is a chaotic, but I guess it's expansive, it is depending on initial conditions, and of course periodic points are dense. So in chaotic situation, infinite number of periodic points and minimal sets can be there. So for better global structure, we need to define this indecomposability in a proper fashion. The natural definition is transitivity. A compact invariant set, lambda is transitive if it has a point whose orbit is dense. And of course, you can talk of maximal transitive sets, and what Snell proved one of the best theorems in this direction is for an axiom-made diffeomorphism F on a manifold M, the non-wandering set omega F is the union of finitely many maximal saturated transitive sets. So John Sema, you can get to that. These sets are called basic sets, and they are uniformly hyperbolic. I have already defined what is uniform hyperbolicity. And if F has no cycles, means once a point leaves an invariant set, it never comes back. That is a no cycle condition in some sense. So there is a filtration adapted to F, that is Mi are submanifolds with boundary having same dimension as M are strictly F invariant, and this kind of condition is there. And each of these basic sets are locally, these are maximum, so these are locally maximum. That means there is an open set containing that these lambdas, so that the iterates, if you take their intersection, turns out to be this. And this feature also is very important, has an important phenomena, that it is robust. You take there is a neighborhood so that any any filtration is adapted to any G. This is the same filtration. This one. This filtration will be adapted to G, and the maximal invariant sets are actually obtained like this. Okay, now as I said, there are two ways it is being done in last say 5 to 6 or maybe 7, 8 years. Not before that. There was a very interesting article by Bonatti at the outset of this century, and wherein he termed these definitions. So tame dynamics. One of the two classified aspects of generic dynamics is referred as dynamics through tame diffeomorphism, which means, what does it mean? The global dynamics is identical to the one given by the spectral decomposition set. Okay, so quickly, what is a residual set? I need to get to the definition. So, yeah, it's very natural. This is very beautiful. Only finitely many distinct homoclinic classes. Then there exists a neighborhood split Q of F in R, so this gives you the robust character of that feature. That if there is a G, then only distinct homoclinic classes will be the continuation. There is a natural sense of continuation of periodic points. So P, F, a neighborhood of P, a neighborhood of F. In a neighborhood of F, there is a G. For every G, there is a unique periodic point of the same index and the same period. So that is continuation. That is the notion of continuation. So that is the G one, PG. That PG is the continuation of P, this periodic point. This is continuation. Okay. So yeah, one actually therefore have this kind of decomposition, spectral decomposition as Spain obtains. This is what Ergodic did. I think this is part of his doctoral work. He did this while he was studying at Quantify. And I will come back. Ergodic therefore finally proves that there is a residual subset R of the whole set of diffeomorphisms, where R admits a spectral decomposition. Then it is robust. So this remark is very important. Omega stable diffeomorphisms, topological stability, therefore one talks of omega stability, that means one looks at only on the non-wandering set. So the dynamics is best understand there. I mean, almost it is understood. Omega stable diffeomorphisms admit generically robust spectral decomposition. In fact, their decomposition are robust in a much stronger local sense. What is that? This is an important remark that the generic robustness of spectral decomposition as a weak generalization of omega stability. So that means this is a genuine extension of robustness of spectral decomposition, which was obtained by Stephen Smith. Mane in 82 has proved that C1 generically surface diffeomorphisms are either omega stable or have infinite diminishing sources. This result does not hold for higher dimension, as has been proved by Bonatti and Viana in their examples. And then there is a weaker question which was asked by Bonatti, Diaz and Puzars in their analysis method of C1 generic dichotomy for diffeomorphisms. Whether generic diffeomorphism either admit spectral decomposition or have infinite diminishing sources, which was proved to be not correct by Carvalho and Morales in the Bulletin of London Mathematical Society paper in 2003. I must talk about this. This is Abdullah has recently. Therefore, one has to go beyond what Smale has done in this. I mean, when we are not in an omega stable situation. So there is a third possibility which is there. There exists a residual subset so that n is greater than or equal to 3, then f satisfies one and only one of the following three conditions. Okay. So I'm sorry. This is second and this is third. So f admits an R robust spectral decomposition, that is this, or f has infinite number of sinks in source and therefore admits no spectral decomposition. And number 3, f admits no spectral decomposition, has only finite number of sinks in sources and has infinite number of pairwise discharge homoclinic classes. Sorry, 2 and 3 are not 50, but this is what the dichotomy we talked about. How many minutes I have? 6 minutes. 6 or 7. I'll come to straight. 6 and 7 minutes, let me talk about this. Well, the interesting problem in differentiable dynamics in recent past has been to study the impact of robustly and persistently dynamical properties, especially expansivity on compact invariant sets. We are particularly interested in homoclinic classes, chain components, and chain different sets. Pacifico and their co-authors actually proved, they were in ETTS 2003, that they didn't assume expansivity on the whole manifold. That is the first result of its kind. Without assuming the expansivity on the whole manifold, assuming homoclinic classes of a F periodic quantity to be robustly expansive, have shown in their theorem C that generically C1 robustly expansive homoclinic classes are hyperbolic. This was the first result of this kind, and then this result was extended by Samperino and Witz, both product of IMPA. They proved in their paper, ECDS, that they actually generalized the notion of, I am talking here of C1 robustly expansive, I am talking of C1 robustly expansive, so they said C are persistently expansive. Robustly expansive, persistently, they are locally, they are talking of local behavior, which is weaker than that of C are robust expansivity, and have generalized results described just now we have said. In their theorem 1, they actually first obtained the dominated splitting. Their passage is like this. They first prove that a C1 persistently expansivity gives you the dominated splitting, and then they talk of germ expansivity in a very natural fashion. They define germ expansivity. I'll talk about germ expansivity, how they define it, and then establish that the homoclinic class is this. Mr. Sakai proved in 2008, and he actually introduced the notion of C1 stably shadowable chain component. Similar in nature to that homoclinicity classes being C1 persistently expansive. It's a very useful notion. Under this hypothesis, he obtained in theorem A that a chain component uniformly admits dominated splitting in a C1 neighborhood of F. The author, he further proves that in theorem C that C1 stably shadowable chain component is germ expansive if and only if the homoclinic class and the chain component are same, and therefore he is able to reduce the hyperbolicity. It's a long paper and he has used several interesting, some of the diagrams there are very interesting. We say a homoclinic class is C1 persistently continuum-wise expansivity. Continuum-wise expansivity we know, continuum is howsoever small continuum you take, imagine an arc, it expands under iteration. That was the notion which Tarun introduced, and there is a series of work there. So, if it is continuum-wise expansive, then this happens. And therefore, and of course, I am including the definition of germ expansivity also. So, this is, if you have a non-degenerate subcontinuum, then any small ball, this is important. You can find an integer n satisfying this happens. So, now the interesting question is, are there enough diffeomorphisms which are continuum-wise expansive but not expansive? And what about the persistently? Actually, so what one can do is, recently we have now been able to, we have plenty of such examples. Easiest one you can imagine is a sphere, and identify the antipodal point, have the projection, and take a linear automorphism on the torus which is expansive, and then you look at the conjugate one. That conjugate one will turn out to be continuum-wise expansive. One has to do some work. This work is primarily due to Dorster from, again, INVA. And once we prove that this is continuum-wise expansive, we already know that sphere does not admit any expansive diffeomorphism or homeomorphism also. So once we have, and because of the construction, one gets that that is also not persistently expansive. So there are a lot of plenty of interesting examples. So this is what has been proved, that under this admits a dominated splitting. This is uniform character of the hyperbolicity. So there are uniform bounds we can obtain under this. So what is this chain condition? So in the C1 stably case, we saw that actually if one looks at the proof, the homoclinic class and the